So on behalf of Shah Institute of Technology, I welcome you all for this session, FDP on electric vehicles. I welcome our guest speaker for this session, Mr. Kartikesh Kumar Shah, Application Engineer in ARK Info Solutions Private Limited, and lead business partner of ANSYS. Sir has already taken one session in this FDP on third day. So we are all known to him, and I humbly request Mr. Kartikesh Kumar Jha sir to begin with this session. Over to you, sir.
Okay, sir. Thank you, sir. Let me share my screen. Okay, so today's we are basically going to discuss about the electronics for automobiles. So why power electronics and what was the basic use of the power electronics? So that we will come to know about this and why we are using power electronics. That is a simple question. Like we want to control our motors, or we basically want to control the thing. So that's why we are basically sir, my screen is visible, na?
Yes, yes, your screen is visible and you're properly audible. You can continue.
Okay, okay, sir. Why we are basically interested in power electronics devices? Like in automobile or in electric vehicle, we can see we have to control whole system or the whole devices like batteries there, and other component is also involved in that, like motor is there, and our we have a fan at our home, and in fan we are using basically 1 2 3 4 and 5 options are there. But if you want to go for 3.5, we cannot go that. So before that we basically want to do analysis, or we basically want to do controlling of a driver by using that power electronics devices. Okay, and and uh, and in that we will discuss about, like we have already discussed these things. We have already discussed about the four pillars, and right now we are interested only in power electronics part. So we will not go in deep detail about the battery and the battery management system, because we have already discussed this battery and we have already discussed about the machine. So today we will focus on power electronics part. So in that power electronics, like what power electronics basically signifies. Power electronics, if you divide your power electronics into switching frequency and over voltage and the thermal reliability and the system optimization and EMI EMC and the life of the system, or the life of the component or the switch, we are basically using it. And going to that frequency part, like if you have a boost converter, for example, and you want to control the output DC voltage, like you want to increase the output DC voltage. So for increasing that output voltage, what we basically have to do, we basically have to provide a switching frequency, and we basically have to provide a path. So for that, what we are doing, we are basically switching on and switching off. So that was the main concept behind the power electronics devices, on and off. And that's why we are basically using PWM technique, and many other techniques are also involved in controlling part. So control with the power electronics is very, very important when we are going for electric vehicle or any automobile or anything. We basically want to control it. And for controlling, we are basically controlling the current and the voltage level. So for controlling the current level and the voltage level at the output side and the at the input side, so we have to we have basically have to look into that. Like for example, some you have a battery, and you are using your battery as a 24-volt battery is there with you. So we have to, and the motor run at 310 and 300 volt. So what we have to do, we just have to boost the power voltage level. So how we can boost it? By using boost converter, converter, and many other converters are involved. But the main problem which lies that if you are using a converter, that converter will also consist of some losses. If you are increase the number of switches, this means number of switches, then that is involved switching losses. And if you are using like DC DC converter is there, and in that DC DC converter you are using inductor and many other devices, so that will also reduce the power factor. If you consider that input supply is AC and you are converting from AC by using a rectifier to DC and then AC to DC, and then if you want to use it as a AC, then you have to convert it in the AC part. So that we number of switches involved, and number of switches will cause the number of reduction in the voltage level. So that also we have to be considered when we are going for switching frequencies, deciding the switching frequency of our devices. Like if you are using and if you are able to generate a normal switching frequency of 1 kilohertz, then the size of your DC DC converter will be very large. So that's why people are going for the 20 kilohertz frequency. And if you are using your hardware device, you have a hardware device and you basically want to use Arduino, and you basically want to use TMS 320F, and you basically want to generate by using the pulse generator, and there are many devices like DSpace is also there for the frequencies. But in the lab or in the hardware part, there are many constraints, like the cost constraint is very important. You are creating a project of nearly for example, if you are a startup company, and if you are or your lab fund is not that much, and you basically want to do hardware testing, how you can do it if you don't have that much amount of money? Like if you have only 4 lakh for your project, and you are going to buy the D space, so you cannot buy that D space part, because that D space is all itself cost 4 lakh or 6 lakh something for the starting range. And if you want to go for a testing of then you have to use, and your budget is low, then you have to use TMS 320F. So that TMS will basically give you a upper edge in costing, and that TMS will basically give you and give you information, and they can, and you can always easily go to that 20 kilohertz frequency range, and you can go above of that, because I have already done that in the lab, and I have also used, like if you increase the frequency, this means you are reducing you are basically reducing the size of inductor. So then if you are reducing the size of the inductor, this means you are reducing the size of whole system. Whole DC-DC converter size will reduce, and the size of the capacitor, so that will also plays a very important role. So we have to take care which frequency my device is working fine, and in that frequency range we just have to only set for resonance part also. We just have to consider that resonance part, that will make a trade-off between the inductor size and the capacitor size. So when you are going for hardware designing part, that is very very important, which component I am using. Like for example, you want to close loop your DC DC converter, because without closed loop, how can you maintain a constant DC voltage at the output side? So that part, when you are going for the closed looping of your DC DC converter, and you are closed looping it, okay, by any means. And for the closed looping, you required, if you have a hardware and you just want to close loop at 20 and 12 volt is there, and you just want to close loop at 20 volts. So for that you required PID controller. This means you want a communication between your system output with the software interface. So that thing also you have to be considered. We have to make the range of that thing, like if you are using TMS or Arduino or many other devices, so then they will basically work for 3.3 volt and 5 volt only. But for the electric vehicle or any other vehicle or any other devices, you are using 200 volts. So for that, what we have to do, we have to use a voltage sensor, and that voltage sensors will reduce that voltage for us. and then we can easily compare it, and we will make that voltage to up to certain range of 3.3 and below that. So that will not basically produce any problem for us when we are going for comparing. And after that, the next thing what we will do, we will basically compare that output result with the certain frequency carrier wave, and then we are, after comparing, we just fed the system to the and provide a switching frequency or the PWM pulse to the switches. So that we also have. And one more thing I would like to add, like if you have a BJT, IGBT and the MOSFET. So for MOSFET, if you are going for below 1000 K and below 20 K, then I would suggest you just have to go for BJT MOSFET part. MOSFET is important. Higher uh, switching frequency is involved. MOSFET is very important. And when you have to go for higher rating of your motor, then in inverter you have to use IGBT. So that also a very important thing when you are going for designing your whole system or whole hardware system. And then we have to check the over voltage protection part. Why over voltage protection? Because over voltage should not go beyond the dielectric breakdown voltage of the system, like breakdown will not be happen. So that then, and for that only we have to consider the over voltage part. And after that we just have to check our thermal reliability of the system. We have to check the thermal limit of my system. And how can we check the thermal limit? By using the ANSYS software, we will basically design our whole system, and then we will do the thermal analysis by using ANSYS iSPAC is there. So that will basically give you information about the thermal level and the temperature range of the thing, and temperature range of the IGBT. So that will basically give me idea about, like if I am designing that DC-DC converter, and that not DC-DC only, inverter part be also, but and feeding my that inverter will feed the BLDC motor or PMS motor. What was the range of the temperature I can expect, and what type of heat sink I have to design. So for designing that heat sink part also, we have to think and we just have to design our system, because the size of the heat sink also a very important part when we are going for our electric vehicle. And in electric vehicle, we have to take care what type of gradient force we are using it when we are designing our whole system. Like I already discussed, in electric vehicle, four forces are involved, like gradient force is there, and rolling force is there, and acceleration force is there. So these forces we have to be considered when we are designing our electric vehicle, and that providing that in the slope, if we are going uphill, the thing their motor required more power. And so for that we just have to check the thermal reliability or thermal capacity of our devices which we are basically using it. And after that, after designing and after all thing is completed, we required for the product requirement, we required a system optimization. Like if someone wants to buy your car, and that car will cost him 20 lakhs. Okay, you have created a electric vehicle and that cost him 20 lakh, but their top range is 90 uh, kilometer per hour to and to 1110, not 1000, 110, 90 to 110. So that range we will, if the cost is around 15 50 20 lakh, and for the 80 to 90 it will cost around 50 lakhs. So people will basically think about that, because people maximum people do not go for top speed part. So we just have to consider that also. And cost is a one factor, and the design is also a one factor, so that we have to optimize it. That system optimization is very important part. And one more thing is the meeting standard, like EMI, EMC, that noise should be reduced beyond range up to certain level and the certain range. And what was the life expectancy of the device which you have created. So life expectancy also we have to be considered, like it should be more than 10 years, because we people do not want to change all the components certainly 1 year and after 2 year, and that will trouble their system. So for that, life expectancy should be in the range of more than 10 year. We are as a standard, we will have to set it. And the next thing, by using ANSYS, you can increase your performance and speed up your model up to 2002x. And we will also design cycle reduction time is also, you can reduce it to 75%. And the total cost also reduce when we are basically finalizing, and we are basically solving whole model system. And I will also show you today like how it's look when you connect the whole EV system in ANSYS. So that thing we will discuss this later on in this session. We will also come to know about like how it's look, so that we will what type of simulation involved in that. So we will also look into that, and how to put the temperature part, and how to use the data sheet part. So I will also show you in that. So we will go for it. Like I we have already discussed these things, like what power electronics requirement from the customer point of view, or from the designer point of view. Like we basically want power density and the lifetime will increases, and how we want this increment with the reduction of losses and thermal derating noise, and the over voltage should be in the range. And for that, we required person from electrical team, mechanical team, and software team, and electromagnetic team. And what they will do, they will basically give us information. And if they are doing their project, and if they are doing their startup or any other thing, so they will basically wants information like what was the system and the circuit design, and what was the reliability of my system, and how we can check the reliability by using the PCB design, and check their the reliability part, and their life expectancy is also there. And for the software part, we will have a embedded control, and then we can easily detect the flow, and easily detect and mitigate that flow part. So we will also do that. And we will also do the magnetic analysis to increase the power density, and the thermal management system is also there for mitigation and detection and mitigation of the component failure, and the EMI EMCs to meet the standard. And one more thing, like for the reduction of certification part is also there, and then noise part is also there. So that noise should be within the range. And like we have a multi domain circuit and the system simulation part. So we have a high power densities devices. So that high power densities and devices will we just have to draw it. And after drawing, the next thing we have to make our circuit, it will work fine. And for the working fine, we just have to connect it with the load part. And when we connect it with the load part, after connecting the load part, we have to design and like load part, and what was the characteristics of the load, like higher rating of the current. And we just have to check the what was the battery. So and that battery should be work within the range of EV. So that also we have to be considered when we are designing for automobile and automotive system. Like if you have a small if you have a small e-rickshaw, and you just want to use that e-rickshaw in your designing part, so for that you just have to make a range from where to where it will basically work. So that range part we have to be considered when we are designing for e-rickshaw. And after that, when we are when design is over, we just have to look into the materials involved. So for that, we will have to check the account for magnetics involved. In that, we have to check what was the cable, and what was the effect of that cable, and what was the electronic transformer is involved. So how we can simulate that transformer part, so that is also involved. And reduced order modeling, and how we can do that, and how fast, and how we can do that, that will work very fast. So for that in we required a required temperature limits and we have to take in, or we have to consider the constraint involved in designing part. Like you can see here, we have a PMSM machine is there, and then load is connected with that, and we are basically having a inverter part, and in that inverter is controlled by space vector modulation technique, and that will be IGBTs are there, and that IGBT will basically help you to control the uh, control the switching frequency will be given to the IGBTs, and that IGBT will control the level of voltage and the current in the PMSM to run fine. So that also required a core simulation, and that also required a faster simulation path for doing the whole simulation. And for that you required a twin builder, and there are many ANSYS software is there, so that will basically give you information up to the range, and this will basically give you the result within the range of hardware design. Like if before going to that hardware design, you don't require PMSM in the hardware, you don't require other things. So first you will analyze by using this simulation, and after analyzing the whole simulation, and if you are sure, okay, so this will work as this part, so this will basically give you a blueprint or idea about the whole system, and this will also give you like what type of software hardware component is required, and what was the rating of my PMSM, and what was the rating of my inverter component. So that will also be decided by using the whole simulation, and this will give you information about like how to set the range, and what type of cooling system I have to require, so that will also come under this. So you just have to read the data sheet for selecting the component. And after designing the part, after designing, you just after selecting the component, you just go for thermal thermal prediction. And in thermal prediction, you can see here a red spot is there. So I will also show you how we can mitigate that. How by using ANSYS you can do such type of analysis, and how this will help you removing that. So we will do that also, and we will also discuss that later. And that red spot we basically want to remove it. And so for removing the hot spot or limit the thermal, like if your whole system is there, and in whole system only one part is getting red hot, so if we do such type of analysis, and if you change that component with any other component, so how this will increase the capacity of my whole system. So so that also we will easily able to address. And the next thing is the embedded control. Like you have to create a model. You have a PMSA model. You just have to create it, and after creating, you just provide a control system. And by providing the control system, you are basically setting the and how this will be behave. So that behavior will be used, and that will basically give you a whole information in the form of code. So that code will be used for the further analysis and the further study. We can use it, that certified code. So that certified code simulation or code generation is there, that will be available in ANSYS. So you will also you use and analyze this. And the next part is to do the EM's certification part. In that certification, we basically are involved like we have a system like this, and in that system we have two things. We are comparing that how to conduct the noise prediction part is there. So for that we just have to go for it for designing, and this will basically give you information about early detection, and this will be, if you early detect it so early, you can mitigate that, and this will also reduce your time and the cost by 20 to 40%. And then you have a PCB reliability system. Like you have a PCB, you can also do the live prediction analysis. You can also do the physical coupling simulation in the single platform is there, and many other options like materials and the component library options are already inbuilt built and available there. So that ready to use model will help you in going for and designing the your PCB label, and this will also give you time which time it will get failure, and the time of failure will be also there. So and you can easily able to predict the lifetime of your whole PCB design. So this will basically about these are the something about ANSYS. ANSYS are basically a number one simulation software for designing and for doing the simulation, and this will basically give you the easily and early age beyond other involved software, and this will basically give you information how we can proceed it. So I will say re-share my screen. Okay, IGBT. Okay, team builder. Okay. Now we will basically look into the how we are going for controlling part. So in controlling part, like BLAC motor control system is there. Like I have already showed you, we have a BLAC motor, and how we can easily create a motor by using the RM expert and motor CAD. So we can easily do the analysis for that. And after doing that analysis, the next step what we have to do, we just have to connect it with the inverter part. And then we have to, after connecting this motor with the inverter, and we required a closed loop or the controller. So for that controller we are using a SCADA suite option. So in that SCADA suite we just have to feed the information, and then we have to analyze that. And after doing that, like a description is there that IGBT inverter is involved. So I will show you how it's look like when we are going for simulation part. So you can see there, and the mechanical load is also connected, and that mechanical information will be given to the motor, BLAC motor. And in that we will basically do the drive, BLDC drive SCADA control options, and these are the SCADA control and the RM expert flux weakening techniques are able. And how the AC motor will look, that AC motor will basically look like this. That was created in RM expert. So and that part is the stator. And now the next we are basically focused on inverter part. So the inverter part is basically how we are connecting the IGBTs are there, and there is 6 IGBT we are basically using for the 3-phase supply. And then we are giving a DC supply to this, and from DC to AC supply, and that will basically help you providing a perfect supply to the BLAC motor. Okay, and then for that we will design the controller for that, and that controller, how we will design that controller by using ANSYS SCADA suite option is there. So that will basically help us in designing part. And the next is the load. What type of load we are interested in? We are interested in mechanical load. So what we will do, we just have to define the load here, torque and the what was the speed. So that we have to for the closed loop we required a rotational rotational inertia and the time dependent torque and the position and velocity sensor feedback to the controller. So that we required it. So that we have to be take care when we are deciding for the load, and if you are changing the load. And the next thing is to provide the simulator time and the reference speed. What was the switching period and the switching frequency? So will be given to our controller. So that controller will take care of the rotation of the machine, and this will give you a result like this. Then this is the speed command and the final achieved the speed. And when you do the that was the starting current, so that starting current is high, and then it is settled when the speed is reached. Okay, so and then I will reshare my screen. Okay, I will share it. Okay. So how we will design the IGBT and the half bridge inverter. So for that designing part, we basically have to open the ANSYS electronics desktop, and from that ANSYS electronics desktop, this will give you will get a look of the power model will be look like this. And from there you can see we are basically analyzing the analyzing the whole system. Like in that you can see a small wire is there. So that wire part and the what was the capacity of that wire, what power, so that we have to be take care when we are going for designing our whole system. Like is that wire will able to basically is that wire you will able to sustain the whole system. And that plate we are connecting, one plate is there and one that plate is there, so that plate part will able to sustain the temperature. So that also will be check when we do the whole simulation part. So for that you can see here collector emitter and the load connection is there, and the collector emitter and the circuit is there. So that circuit we are basically designing it in the structure form. So we are basically using the DC plus DC minus option is there. Red one is for plus and the blue is for minus, and we are connecting it. So that connection and how that will basically help you when we are going for final designing. So how this is the one leg, and another leg we can also the same we just have to create the same leg, and we can also use that leg for the designing our inverter part. So that leg when we go for design for the single phase inverter, so it will look like this, and that is the positive and that is negative part. And we have to check the thermal analysis part. So we'll first draw one by one, and after drawing that whole system, where we able to design, like if we have selected the material as aluminum and copper, so that we have to take care like what how we can select the materials for connecting wire and the for connect selecting the material which we are using, and what type of heat sink is required. So we have to take care all the things when we are going for designing the power electronics devices. uh, like the 3D modeler option is there in the ANSYS. So that 3D modeler option will help you, or the zoom option will help you basically decide like how to select the face and how to select the model, which part you are focusing on, so that you can easily do it. Like we are interested in select this here, so we will select that is only. And if we are interested in selecting the B face, so we are selecting that B face only. So we can only select that part. And after selecting that, and after designing the whole system, we just have to analyze it. So before going to that analysis, like you can, we have already discussed it, and I have already showed you the blue color metal is for DC minus, and the green plate is phase out, and the red is basically for the positive, DC positive. And after selecting the hole, the next we have to analyze the pins, and after analyzing the pin, we have to connect it or make the connection. Aluminium wire wound is there, so we just have to just connect it, and after connecting, like we are interested in only that connected phase with the aluminium part. There is a connection, so we have selected only that phase only. Here also we have selected, and in the whole model we are selected only that is the IGBT down, and that is the IGBT ups, so upside and downside. So, and after selecting the whole pages, the next we just have to uh, model it, and after modeling we just like we have connected it to the heat sink. Okay, so after selecting we just have to proceed this like this, and after selecting like gate down sink is there, and the sink and source is basically input and output. So we just connecting it and select it, and the next after doing that whole analysis uh, one by one, and then we have upper metal, and we have a traces the like blue and color and the green color specify the different things. And the next step, like metal lower part is there, and the trace part is there. So, and after doing that we just have to supply the DC minus name is there for the sink, and after sink like DC plus option is there, and the next we have to, and after the next steps I am just fast forwarding these steps. So when we will design, it will take time, and after designing we just have to go for simulation part. And so we will have to set the name, we have to set the frequency, like here it is set it as in 300 megahertz. So we can also set it, and we just have to set the solution setup, and after selecting we will able to calculate the uh, DCRL resistance value, and then we have to press it OK, and then we have to validate our whole model. And after validating our whole model, after validation we have to just go for checking QR how and what we have designed it. So you can see here the colors, that colors will basically provides you information as a JAC is there, and that will basically ampere per meter. So that will basically gives you information about, and you can also select like linear values there and log values there. Log value will basically give you detailed information. And the next you can check the colors, and by using the colors you can if you find it any problem in that designing, so you can also change it. I will also discuss one of the answers customer is there. So you can see here that strip part. So what they will do that, and you can see here the width of the strip here and here. So that will be about thicker than this. This is a thick part. So they are getting a more temperature here. So what they have done, they only change this much, and that will basically increase the capacity of whole IGBT system. And that increased system will help them to use the same IGBT, same model for the higher rating. So that will basically enable them to use the same material they have. They will also use, say for the BLDC or EMS motor. So they don't have to go for higher rating of the whole system only by changing the width of this, because for the transient period of time they are going beyond the certain limit or the certain ranges. So that's why you can easily design it in the answers, and you can easily decide it how and where I have to make the changes. So and after doing the whole analysis, we just have to like here it is the resistance in 1 hertz, and we are setting all the information, so we will have to set it. So and then the next step is to get the results like this, like DC plus, DC sources, and ADC. So this will give you in the frequencies there, and in their ARC option is there for the frequency. So I will reshare my screen for going for main designing part in Twin Builder. Okay, so I will show you how it's really look in Twin Builder. Okay, so first what we have done, we have created only one IGBT, single IGBT is there, and what we are doing, we are feeding with the data sheet what we have. So let me show you the data sheet which I am referring. So which IGBT we are basically preparing is this. Okay, so we are using the this IGBT KIKW75N60T. So that you can also do for your example. For example, what you have to do, you just have to go to that data sheet, and from that data sheet you will get information, and you just have to put that information to the system or the simulation. So that will basically give you a perfect result for your designing part. And if you don't do and if you don't proceed like this, this will create a problem, like you will in a haphazard, and you will not able to decide like I am doing correct research, or I am doing the going to the correct direction or not. So that we will have to take care when we are going for final designing part. Like you can see here, the maximum junction temperature is 175 degrees Celsius. So that we have to take care. Okay, so that was the range of the temperature. We cannot go beyond that thing. So we have to set that part. So like that, you can see here short circuit withstand time is also there. So we just have to look into that. And the next we have to check it, like and what was the rating. So you can see here, we have selected that for 600 volt and 75 ampere CIC, and that packaging. So that would be have to consider it when we are going for final designing part, because final designing should be look, and because you are using that component only, so you can also use it. Okay, so that model I am using, that material is I am using it. Okay, so like you can see here data sheet, and in that data sheet you will get a uh, get resistor and the collector current, and you also check the temperature, junction temperature, and what was the other thing. So you just have to look into that, and you just have to cover the whole things. And after doing that, then after selecting all the ranges, go for designing it. So when you go for designing part, you can see here we have set it temperature for this ampere range, and the frequency 1000 for the gate pulse. And then I am checking it. Okay, so what was the average? So I will show you the result, so that will basically give you a clear idea. And what was the junction temperature it will reach when I will run it. So I will run it for 40 millisecond. So we are getting a junction temperature of 310, And if you are going for that junction power, what was the losses and what was the power it will generate? So that if you click on that, like you will get a junction power, and in that junction power for that particular time, 40 millisecond, when switch is on, so you are getting a temperature or the junction power like this. And what was the IGBT, IC and VC characteristics. And you can see here one more thing, like let me zoom it. So you can see, yeah, this part, switch is on, and that part, what we are doing, switch, making the switch, and when switch is on, voltage across it is zero, and going to that zero. So that part will basically create a problem when we are going for designing, because that switching loss option is there, because you are getting a current, you are also getting a some voltage here. So that voltage into current will produce some uh, losses. So that losses we also have to be considered, and that losses will be considered as switching losses. So that part also, when we are deciding the component and when we are with the extended capacity of that short circuit part, and so that also we have to be considered. Like we have one leg for the three phase inverter, we have two IGBTs. So that IGBT will not be switched on at that particular instant when they are at that above IGBT, and below IGBT is there, and above IGBT should be switched on, and below IGBT is also switched on. So that will create a short circuit. So that also we have to be take the, and some time, some delay time will also be there for switching on and off of one and the other. So we you can see here, we are basically getting nearly 40, up to 40 in the range. We are getting the value of, like if you multiply the current with the voltage, we are getting a losses, switch losses. So we just have to check into that. And like you can see here, the junction power, junction temperature, and so for the one we have decided. And the next step is to connect it as a three phase inverter. So we just have to connect it with the three phase inverter. So what we have to do, we have to use the same IC, and we just have to connect it in the form, like I will show you. Okay, no, first we will go for this simple system. In that simple system part, we have a AC supply is there. Like you are interested in creating a charger. If you are interested in to creating a charger for the electric vehicle. So for creating a charger for the electric vehicle, we have a AC supply. So for creating a charger for the electric vehicle, you have a AC supply. And from AC, we want DC supply.
मैंने ग्लोचो मारे तो लाइट वो भी लाइन
Just participants to mute
Hello, can you mute? Hello, can someone mute?
the participants.
Hello, can you mute?
Right, sir. Can you mute the participant?
Okay, I think it is muted.
Yeah, sorry for the inconvenience. You can continue, sir.
Okay, where okay, I am, what we have to do, we are creating a charger for our electric vehicle. So creating a charger, we have a three phase supply is there, and from the three phase supply we are basically giving to the diode rectifier is there, and that diode rectifier will give us a voltage, and that voltage we are using a capacitor to make the voltage stable. and to make the voice constant as a filter, and then we are providing this to a DC supply to the inverter part, and we are connecting a motor, and load is connected. Right now we are not making a closed loop, or we are not controlling it. We are simply giving the information, and like we have AC supply, and for the constant information, we are not controlling the speed of the motor, because our motto right now is to check the how three-phase inverter will work and what was the result I will get it. So and we are using a gate pulse here for the one leg is there, so we are using the three leg for the three gate pulse there, and the gate pulse will be given. And after doing that, if you run that model, you will get a phase current. So for phase current for the single phase, you will I will zoom it little bit. Okay, so you will get a result like this. So phase current option is there, and right now what I am doing, I am not using the constraint of thermal. I'm just connecting for this simple, like this way. If I have idea, I'm using a simple inverter, and I am connecting for inverter. I am using a three phase. So what was the result I will get it? So that you can see here. The what we are doing, we are using a AC supply. We are connecting it to the rectifier, and from rectifier to DC supply, and from DC supply to the inverter, and then inverter to the motor board. Okay, and that also we like we have simply used a motor, but by using the RM expert, we can design our motor, and that designed motor will be imported to that this uh, twin builder part, and there you will then, like I am using the IGBT, and we are basically exporting all the information of IGBT from the data sheet, so that will basically give you a correct result. So, and if you also import that motor part from the designing information, so you will get a correct result like a hardware, so that you can easily do it. So before going to like now what we will do, we will the thermal information to our IGBT also, and then we will check. Now, okay, now we have an inverter with IGBT and the motor load, and I have given the thermal information, and thermal package is there. So I am using that thermal package, and from that thermal package, I am giving the information. Okay, thermal information is also in, and if you run that simulation, it will hardly take 1 minute. Okay, simulation is over. We will go for result. Like what result we are getting for the phase current. So we are getting the result like this for the phase current, and for the line voltage, we are getting a result like this. Why we are not getting a perfect straight line here? Can anyone from the participant answer this? Why we are not getting a straight line and line to line voltage? And for the IGBT thermal characteristics, we are getting a result like this, that rise in temperature, and then switch off, then rise in temperature, switch on, switch off, switch on, switch off, switch on, switch off. So sorry. So we are getting a like the IGBT thermal characteristics we are put it, and after that you can analyze it like your IGBT will be reached up to this temperature range. Then we have to design our model, and we have to design our whole system like this, and we just have to take care of the temperature also if you run yours for the particular period of time. So then I will show you how we can design it in step-by-step process. So I will reshare my screen because I have recorded that part. So what we basically interested in, we are basically interested in Q3 by using the Q3D extraction. We can like we in the simulation part in the PPT I have shown you, we are getting a result like this. Like for the ampere per meter, we are getting a result like this. And what we are basically interested in, we like you can see here a red hot spot is there, and we are also if this is for the EM loss, electromagnetic losses, and the losses result, and this is the temperature result. So the temperature result you can see here, the wire is heated at this point, and wire is heated at this point only. So we have to look into that by using the ice pack. We can easily predict that, and after predicting we have to mitigate that, we have to remove that. And how we have to remove that, either we can use and change the material, or we have to increase the length, or we have to increase the thickness, or we have to provide a cooling fan, or any other methods are involved here, so you can use it. So like inverter is there, and then you are getting a three phase DC AC supply is there, and we are using IGBTs. Then that is the AC motor, and from transformer to rectifier, rectifier to inverter. So we are interested in simulation of power converter, and that power converter using the you will get a current density plot on IGBT like this, and it will look like this. And now how I have already showed you, like this will look when you are open in ANSYS electronics desktop, the half bridge inverter will look like this only. So we just have to solder it, and subtract is there, and the base plate for the heat sink. And then we have to put the whole system in a frame, and then we have to check DC minus, DC plus for the DC supply, and for the phase. Then for the get down, get up. and we can easily edit the source like DC positive and DC negative to the phase. And in the history tree, you will get information like selection of the material, aluminum, polythene, and then by using the ice pack, we will able to predict the temperature. We just copied that model which we have designed to the ice pack. Aluminum, and these are the component diode and the IGBT. After selecting, we have to assign the thermal. First, we will go to EM losses, electromagnetic losses. Then we have to simulate the design, and then for the simulation, we have to press OK. Then your model is created in ice pack. Select the face. So I will fast forward this whole step, like how to do these analysis, and then we will go for analysis part only. So we have to press analyze. Okay, and then I will show you the next, and the next step. After designing and after selecting, we have to plot a temperature. And by the temperature, you will come to know the what was the range of the temperature which we are getting. Like you can see here, the temperature range from 30 to 114.51 in degrees Celsius. So that is the maximum temperature which we are getting it here. And we just want to reduce the range of this temperature. Our main focus and our what we are optimizing, we are basically focused on temperature optimization. So we will basically going to optimize our temperature. So then for that we will optimize it, and we will reduce it. So for reducing, we have many options available. So for that, we will change the material. One option is there. We can also change the width. So for that, we just have to select that part, and then we can compare it. Like first one is Q3D EM model, and second one is temperature model. So these are the part of the connection. And these are the wires. And that is the point of main concern, where which we are getting a temperature maximum, because our we have already used that, and we are using that particular IGBT which I have shown you the data sheet. So for that only we are designing this. So select that object, and then you can see the area. And then we have to select that size of the area, and from there we can do the, and we will change that, and then we will recalculate and reanalyze our whole model. So first we just have to save, and then we have to reanalyze it. Now we can see the temperature will basically reduced, and how much it is reduced, like 100, that earlier it was 114, and now the maximum temperature is 93.54. So similar analysis you can also do for the other components and the other things like reduction of temperature, reduction of the size, and this reduced temperature will basically help you to select a heat sink size. So that heat sink size also you have to be considered, and you have to be also take care when you are going for designing. Like I have showed you for the IGBT, you can also, like we have a three phase supplies there. So six leg, three leg is there, and one leg contain two IGBT. Sorry. Sorry. And but we are interested in only if you are interested in only one switch, so we can easily do the same analysis there. And in that you can see the temperature is set to 93. So you why is this, you can also design your IGBT MOSFET or any other if you are interested in, and you if you want to do the analysis like temperature analysis or any other thing. So you are getting the maximum temperature here is 93.54. So we can also thermal specification. And this is the modified, and this is the original. And in that modified you will see the original 134, and in that we are getting a 113. And for the next, like we are interested in now changing the temperature range. Now we are getting the 93 for the wire part, and we have to connect it as a three phase. So we will select, and we have to provide the cooling system also. So for that we have to assign boundary, and then we have to press OK. Then we have to select the base, and we just have to copy and paste it, like create a duplicate of the same which we have already designed it. So after duplicating, we just have to place that, and then we have to make the connection. And this is the water-based cooling system which we are using here. So we just have to assign thermal, and then we have to press use this project, and then we have to select the source design, and we have already selected earlier, so we don't have to change that. And now the water is also selected. A water cooling system is also selected. Water in, and we have to set the velocity meter per second for the water, and we have to set the water out. Then we have to analyze it, and then you can see here what was the temperature by using this water jacket or water in and out. We are setting it, so you can also analyze it and you can also change the material of the water, like from water to oil or any other, like we have already discussed in the EV starting of the EV sessions. Like we can use the cooling system according to our need, so we just have to set it. Then we zoom in and you can see here. So that is the main area of the concern. That red is phosphate. So we have to, if you want to change or if you want to reanalyze it, you can also reanalyze your whole system and check your system is working perfectly or not. This will basically a animated part. So the particular range. So from that you can easily check your model. And after completing this system and the whole analysis of your IGBT part, we will connect already connected with the in the thermal form. And now the next step is to we will go for full EV model design. Like we what from the starting what we have did, we just selected IGBT. After from the data sheet we created a IGBT and we have fed the information in the IGBT. The next we have created a 3-phase supply, and from that 3-phase supply to the DC from using rectifier, and from the DC to the inverter. And what we are doing next, the inverter to the motor, and now we are complete modeling with the inverter, and that will be fed with the thermal part. And then we will go for analyzing of the whole temperature part also in by using ANSYS ice pack and the Q3D extraction. And from that Q3D you will get the value of resistance of the wire, you can inductance and the capacitance part. And after completing all the things and after deciding like what type of inverter we are going to design it for our electric vehicle. So the next step is to connect that inverter with the EV part, electric vehicle part. So for that, we will go for complete simulation of EV model. So first, I will show you the example which I have already shown you. Like first, we will go for PMSM part. Now inverter is created, DC supply is there, and we are controlling our inverter. By using that inverter part, we are controlling the speed of our motor. Okay, so zoom in little bit in the motor part. First, we will check it. Okay, so that inverter, that motor is by using the ANSYS, you have created a motor in the RM expert. And you have kept the all the information, like what was the size of the motor, and what was the other information about the motor, what was the rotor, and it is a SRM switch reluctance motor or PMSM motor, what was the size of the permanent magnet. So you have fed all the information and you just analyzed your motor part. So motor part is over, and after that you analyzed it. And after doing this part, you just analyzed your inverter part. And after analyzing inverter, the next step what you have done, we are controlling the speed of the motor. So now correct motor is designed, and you have also checked using the motor CAD. By using motor CAD you have confirmed your motor. Now you are connecting it with the inverter, because we have done so much analysis on the IGBT part. So we will come to know about what was the temperature range it will achieve. So after doing analysis, rigorous analysis, we just used that IGBT here. And after doing we are simulating it, and we are getting a result like this. So I will show you the results, and then we will go for complete EV modeling. And now we are the okay. So I will show you the first the control signal which we are providing. What we are doing, we are basically providing a control signal like this. We are using a hand signal of a triangular wave, and we are cutting it according to our use, and this will give you a result like this. And then you can show the line current value. Your line current will should look like this, and this one is for the inductor current, IU inductor current, and the inductor for the phase A, phase B, phase C, and then I will show you the torque value. So you are getting a torque like this. So finally, your motor is decided, your inverter is decided. Now we have to go for complete modeling of EV. So we will go for EV part, and we will so first I will go to that twin builder. Okay, hysteresis, here we are using a hysteresis band control. So you can also use different techniques for the controlling of your PFSM, PLDC. You can also use it, induction motor, and you can also use switch reluctance motor. But for the example, I have used PMSM, and the next step is to go for it go for EV application part, complete EV. So now in EV, we have a driver. Okay, so we have a driver, and your battery is being controlled, and so for that we are using a controller, battery controller. BMS is also there, and that will be a motor controller for the motor controlling, and we have connected it with the motor, and that motor will give information like what was the length of the tire, and what was the length of the, so we are feeding the all the information in that, and then we will simulate it. So and that is the driver, and that will basically look into like when we have to accelerate and when we have to decelerate. So before going to complete EV simulation, or before going to complete EV process, so first I will like to add something here. I will want to show you the result. So before going to that result, like duty cycle, duty or the duty cycle is involved in that. Driving cycle is also somewhere it is a driving cycle, like Indian driving cycle, USA driving cycle is involved. So for checking your ICV, your whole motor, or checking your whole electric vehicle, we basically use a parameter driving cycle, and that parameter driving cycle will be given here also. So we will put the driving cycle, and after putting the driving cycle, we have to create a controller. So I am using here as a VI controller to control and track that driving cycle, and we will also check for the what was the battery state. So if the whole simulation will run, you will also come to know for that driving cycle, and for that particular what driving cycle is basically, driving cycle is basically give you information meter per second in the for the particular distance. So that will be provided by your driving cycle. So that will basically give you information, and from there, so I will so from there you will come to know like what tracking I'm using, and what type of controlling we are using to track the model, so that will be working fine or not. So that you will also come to know, and that you will also think about it. So like I will one more time I will explain it like the whole process. First, DC supply is there. Right now we are not using charging point, and we are basically thinking that if our battery is charged up to 70% or some range, it is charged, and that will be fed to the motor controller, and then motor controller will that motor controller also contain an inverter part inbuilt in that, and that inverter will be fed our PMSM motor, our DC here. And then we just have to check the DC. Right now we are using only a DC machine, so the the machine is there. And then we are using a brake system is also there for the controlling. And one more thing I would like to add, like if you are going to the uphill part, and your whole system does not contain a regenerative braking part, and regenerative option is not there. This means when you are coming down, you are wasting all your energy which is lost in the coming up. If your regeneration is 50%, then if X amount of energy will be used by a vehicle for climbing up, will be gained up to 50%. If your regenerative braking is efficiency is 50%, so you will basically cover, or you will also you will also get or charge your battery by using that regenerative part. So for electric vehicle it is necessary to have a regenerative part, but for the simplicity I have not used it here. But for the electric vehicle part, that is the main beauty of the electric vehicle, so you just have to use that regenerative braking. This means when you are climbing up, you are using X amount of energy. So when you are climbing down, and if your regeneration is 100%, this means that cost, climbing up cost or the discharge of the battery will be recharged. So then you just have to not waste much amount or much power or the energy when you are climbing up. So we just have to take care of that controlling part in that regenerative part also. So, but for the drive cycle which we are using here is not considering the slope. We are only using the that flat road is there, and we are running our model. So for that, I will analyze the whole system, and then we will check what was the result we are getting. Now, like we have analyzed it, and now we will check it out. What was the tracking? Uh, we are tracking able to track it correct or not. Like a given reference velocity versus model calculated vehicle velocity. Like we have this driving cycle which we are using. This is basically a US driving cycle, and this driving cycle is basically meter per second by second. We are basically using that driving cycle, and we are tracking it. Now we are using, I am using here as a PI controller, so we can also check like it will able to easily track it. But in some point it is not able to track it. Like at this point it should be reached at 0, but this is not reaching at the value of 0. So we have a scope of improvement for the tracking part, and we can also check it somewhere. It is not able to track up to below point and up to above point. So we just have to check it, and we have to create a controller that will basically effectively able to control it at that range. And we can also have to go to that like calculated velocity and what was the state of the charge. That SOC is very important. This is basically a state of charge. Now you can see here I am using a battery of nearly 71% or 72% charge, and for the whole driving cycle range up to 1400 second, it will discharge up to 30. So before it is increasing and decreasing, and we are not using a regenerative part here, so it is not able to charge. We are not able to charge our battery. And these are the iteration we are basically using. So go to that EV part. Okay. So what was the scope you can see here for the research point of view? You just go for regenerative braking. You can also improve the switching losses by using the power electronics devices. You can create a perfect tracking devices, so that will track the speed. You can also go for sensorless driving for the VLDC and PMSMOs. a machine. So sensorless technique is also important when we are going for designing part. Like if your sensor is not working fine, like if you have a VLDC motor and you have three sensor H1, H2, S3, and that sensor will be failed, so that will also a very point of consideration. And you can also design your, after designing the whole system, you design EMC model is there. So where there you just have to uh, correct it, uh, that will like 10 and 20 electric vehicle is running in the road, and you are giving information to the cloud, and that information will not be hacked. Like you, as you are running in electric vehicle and you want to increase the speed, and you are giving information like increase the speed up to this range, but your vehicle is just stopped at that time, so that will cause the accident. So that also why we have to take care of it. And one more disadvantage of the EV is the battery system, and that is also advantageous. And what it will also give a disadvantage, like if you have a petrol engine and you have a EV system, but for the petrol engine, if you are left with the 1 liter of petrol, you can run your vehicle at the fast rate. But then you have a battery system and your battery is going up to down up to below 15, 15, state of the charge is 15, so then you cannot able to accelerate your vehicle up to certain range. So that will be the disadvantage with the EV system when we are using the battery. So we have to make, or we have to create a battery management system, and many other components look like this. So that will basically, and the EG battery swapping option is there. So we just have to look into that part also. So and I would like to add some more points here. Like if you have a whole electric vehicle system, but your power electronic system is not efficient, and the cost of the whole system is very high, so that will also not a feasible point when we are going for designing of the hardware system. And and now I am open for Q&A, so we will just look on the chat. Is there Q&A option is there?
Thank you so much. We'll begin with the question answers session. So I request participants, if they have any question, they can put in chat box or they can unmute and ask.
Yes, sir.
Yeah.
Even they can also ask related to in EVs, they are able to ask any question related to that. Like if they are going for prototyping, and if they are going for hardware designing part in power electronics devices, I will also discuss it here.
I have few questions. Um so the one question is like in the IGBT, the simulation what you showed. So the
Mhm.
model you made. So there you talked about the temperature and some methods to improve, like you are increasing the width of those contact plates.
Yes, sir. Yes, sir.
So there, if you want to see what is the effect of, let's say, cooling method. So for example, we are putting some fan or convective cooling type of system. So how can we
Okay.
do the analysis?
Like I have already showed you, we are using a water system, water cooling system there. And in that water cooling system, I am inletting the water at that particular velocity. I have already shown you that you
Yeah.
can also use the different different cooling materials also.
So there we need to create a domain like we
No,
do
no,
in
that
low end.
pre-modeled option is there. Only you have to change the material. Like I have you select the water, you just have to select the material of that density. Like I have put the value of density of the liquid, so that liquid you have to change it.
If we want to develop, let's say, a custom cooling mechanism where
Ha, ha,
we would place this IGBT on some other platform, some other, let's say, cooling method, so
ha,
that
ha.
user defined size or shape of that.
Option is there,
Yeah.
sir. Option is there. By using the CFD tools option available in the ANSYS CFD. That CFD you can all customize the whole system, like whole design you can change it.
Okay. And then we can integrate both the twin builder and
In that
fluid.
twin builder, like I have already show you, like I have designed a motor. And likewise, you can design the whole system and then you just put it here. Like that motor part is there. So that motor part is designed in different software. And from there we have used this. So you can also import it and integrate for the co-simulation.
Okay, okay. Another question I have is like
Yes, sir.
the lines which are connecting these particular IGBTs, motors, and then the batteries of this model. So similar kind of thing I have also seen in MATLAB Simulink. So
Yes, sir.
there, yeah.
But
So
in MATLAB, we cannot able to do the we cannot do the 3D analysis. There we have only a single line diagram is there.
yes, 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 right, right, right. So here these lines signifies the electrical signal.
Yes, sir.
Right? Okay, okay. And one more question, can we do a multi-physics simulation like part of that you have already
Yes,
explained?
sir. I
But
already explained. We are doing basically multi-physics here. Because
yes, yes,
without doing the multi-physics, we
mm,
cannot go for designing of EV system.
yes. So here, let's say we want to, let's say, simulate road data also, other than drive data,
Yes,
and
sir.
then some drag coefficient is there, or some jerk, or let's
We
say
have to
some
we
powertrain.
have to fade such informations like rolling resistance because
Yes,
road is not flat, na always.
right,
So
right,
we
right.
just have to put that data also.
Mhm. And one more request to you, like most of the participants here, they are not directly from the power electronics background. Let's say most of us
Mhm.
are from mechanical background. So
Okay,
what would
okay.
you recommend to start with? Like we want to do this simulation, and before that we need to study also some basics so that we
Yes,
would
sir,
be
that is
comfortable
very
in doing this.
important.
Yeah.
That is very
So
important because if you are from a mechanical or any other background, but you have to control the motor and control the many things are involved. So for controlling, you required power electronics.
yeah. So to
And so for starting I will tell you like you just have to go to like I have showed you the how I will proceed. First we have to select the component and how like IGBT, there are many IGBTs available, but for that particular load like we have to select that 600 volt is there for our motor. So we will select that particular range of IGBT, and from there we have to download the data sheet, and from the data sheet we have to proceed further.
okay, okay, okay. So
Or for
basically,
the uh-huh.
in simple terms, let's say I have to as a mechanical engineer, I have to study all the basic components needed for electric vehicles, how they
Hmm.
work, and then start with their simulation. Am I
For
right?
that you can refer the book like VS Vimra for the simple starting
Okay,
electric
okay,
power
okay,
electronics devices.
okay, okay. Thank you. One more question is there in chat box from
Okay,
Mr.
sir.
Naeem Tansildar. From your simulation, battery discharge, the acceleration not getting. Why not maintain voltage regulator?
I have not used it for the simple diagram. I have only generally I have created that simulation. I have not considered that part. So you can also consider that.
Okay, okay. So any other questions from participant side? Okay, so we'll conclude the session here. So I thank all of the participants, and especially I thank our presenter, Mr. Kartikesh. So
Okay, sir.
that was a
Thank you, sir.
very nice presentation. We showed how to the basics of power electronics, then simulation of IGBT, thermal analysis, complete EV simulation. That was a very nice session. So I thank you again, and I thanks all the participants for patiently listening to this session. There is a feedback link in the chat box. I request everyone to please fill the feedback link, and I request all participants to turn on the camera for a while so that we can have a nice photo.
I am
So
also sharing my email ID. So if you have any problem, you can contact me on that.
sure, sure. So I request host to take photos and just inform
Kartikesh, sir,
so that.
can you stop the sharing?
Okay, sir. Okay.
Yeah, thank you. Sir.
Sir, please provide the link of simulation software.
Yes,
Hello,
sir.
sir.
Done, sir.
Okay. Okay. Okay, so we conclude our session here. I thank participants.
Hello, sir.
And
Yes, sir. Yes, sir. We will provide the
Ah.
link. I'll share the link in WhatsApp.
Okay. So we announce that we conclude the session. Second session here will start for the last session at 2:30, and please be there in the last session. And after that, we'll be having a quiz. So thank you, everyone.
My video, my video. Yeah.
ऐसा दोनों उंगली सर की एक ही उंगली